I don't know how many of you have heard about it, but it's probably you all heard about Carl Zeiss. So Zeiss is for your glasses are made of the Zeiss glasses. So these are the optical companies. So Vienna is quite famous for optics and the related industry. So, so let's see. So why this talk about artificial neural network or physics informed neural network? So what is the motivation and why now? So artificial intelligence, so even though it has been here since the 1950s, it's in the last decade that artificial intelligence has really impacted our day-to-day life as well as the economy. So this is a poster from the European Parliament, if you can see. So it shows the various areas artificial intelligence is being used. Probably in our mind, artificial intelligence is the Terminator guy, but we are far away from it. But otherwise, in all of our daily aspects, this artificial intelligence influence of AI is there. For example, your smartphone, so your digital assistant, Siri or the Google Assistant, it's based on AI. Your spam filter in your mail, it's AI based. And you have these Internet of Things like web-connected vacuum cleaners, refrigerators, washing machine, and all of these things. For autonomous cars, you need AI. So for online shopping, for protection, cryptocurrency, or all these things, cybersecurity, you have AI. And for smart farming, and you also have robots in factories. So you can see that this is just a small glimpse of how AI is affecting our day-to-day life. And also during this current pandemic, for the fight against COVID, you also AI is there, because when you make this thermal imaging, AI is deciding how to, if you are with fever or not, and so on and so forth. So in short, AI is everywhere, and it's affecting all of our lives. So let's get on first with the terminologies. So we hear artificial intelligence, machine learning, deep learning. So what is it? So artificial intelligence, the word was coined by John McCarthy and colleagues in 1956 at a conference, at a computer science conference in Dartmouth. And this is how they've defined it. So AI, it is the science and engineering of making intelligent machines, especially intelligent computer programs. So it is related to the similar task of using computers to understand human intelligence, but AI does not have to confine itself to methods that are biologically observable. So this was just a definition they tried to give for AI. And so now we have like AI, machine learning, and deep learning. So machine learning and deep learning are the subset of AI. So by machine learning, what we want to do is we want to make softwares and tell computer to do something with, we want the computer to do something without explicitly telling it what to do. So it has to learn from its past experience and such. So this is just, so if you read about it, you can find a lot of definitions and terminologies depending upon which field you are. So, but this is like a general definition. So today I will talk about artificial neural network. And after this talk, hopefully you should be able to build your own artificial neural network for a regression problem. And you will get some familiarization with Python and TensorFlow. So Python is a programming language, and TensorFlow is a machine learning library from Google. And you have a general idea about physics-informed neural network and whether or not you can use it in your own research. So hopefully I can do justice for this scope. So what is artificial neural network? So it's a machine learning program which is based on this biological neuron. So we want to mimic the biological neuron, but we try, okay, it's not yet, we are not yet there, but we try to mimic it. So let's see. So this is a biological neuron. So so this is a neuron which is trying to form connections, and you can already see that it's a very complicated process, but we try to try to use this ideas, these connections that all neurons are connected and information is passed on in certain way. And we try to use this to design our artificial neural network. So the simple neural network has looks something like this. So you have an input layer. Here I have many neurons in this input layer, and you have an output layer. And here there is only one output. And then you have several hidden layers, which have several neurons. And then each of this neuron is connected to the previous neurons in the previous layer. And then this connection has some weights. And I will show you how it is connected. And so we try to mimic the biological neuron, and we see what we want to do. So let me explain with a single neuron. So the single neuron, you have this single neuron, and it's connected to two other neurons in this example. So the input here is X1 and X2, and I've connected this neuron to this single neuron here. And you can see several things which I have written. So there is a weight to this connection, and there is the output, which is the f of y. So what is this neuron doing? So we calculate first y, which is not the output, and which we call it as the weighted sum. So what do? We take the input x1 and multiply it with the weight w1, and then add the second neuron x2 and multiply it by its weight w2. And if you have several other neurons, you just sum this up, and then we add the bias. So if as physicists, we know what this equation looks like. So it's an equation for line in a multi-dimension, right? So, but still this is not the output. Now we have this weighted sum, and then we pass it through an activation function. So this activation function are certain kind of functions which we want to take from the biological neuron. So that I will tell in the next slides. So what we now have is y, which is a sum of this inputs multiplied with its weights plus a bias. And then you have an output value, which is passed by an activation passed through an activation function. So how does this, so this, we have several kind of activation functions which we use in a neural network. For example, let's say sigmoid, rectify, linear function, so on and so forth. So these are usually some kind of S-shaped functions. And I will just show you what it looks like. So here is the familiarization with Python. So it's a simple code. So if you simply load whatever modules you need. So you load the NumPy module, which is the numerical Python. And here I loaded the matplotlib for plotting. And then I define what is X. I want to plot the logistic function, which is 1 by 1 plus NP of exponential of minus X. So this is simply the code. I mean, just to show, just to familiarize with the Python syntax. So the next slide I will show. So this is how it looks like. So I plotted the logistic function. So it's a step function, right? Sort of step. And ReLU, it's also something like this. So for all the X negative, it's 0, and then it gets value for X greater than 0. So what we want to do is, from biology, we understand that the neurons fire after a given threshold. So we want to replicate that by some mathematical function. So ReLU is the commonly used activation function, but you can use different activation function depending on your problem. So, but ReLU is mostly the commonly used one. So now we have some idea, we have to write the weighted function and such. So let's try to build a very simple neural network. So we have some data, which I assume is of the form y is equal to x squared. Simple problem. So I create a neural network with one layer and one output. So, and I want to do a prediction that what would be y at some x value. So these kind of problems are called regression problem. That's where you are making the prediction. So then it's like you want to predict if it will rain or not rain or such like that. Then you have the classification problem where you classify objects. So here we will deal only with regression problem. So just to tell you, so the classification problem is like if you want to classify if it's a fridge or something, washing machine. So I mean, if you want to classify things, you use the classification problem. So to start, we need to collect and prepare the data. So it's the most important thing we have to do. So data usually you get through your experiments or some observations, or you have a lot of data you can collect, and then you want to predict how it will be. So here, to start, we will load all the modules, which is the TensorFlow, which I load as TF, and then of course NumPy for plotting, Matplotlib, and so on and so forth. And then I create a fake data. So I want the data to look like x squared, right? So first I define x. So I have like 550 data points ranging from -50 to 50. So this would be the ideal behavior of the data. So I select fake data from this ideal set. I collect some 55 data points. And then I say that this is your data which you got through your experiment or whatever. So now the data is very clean. Usually it won't be very clean because you will have noise and such, but I'm not adding noise just for convenience. But so now I want to see what is the behavior of the data. I know that it should behave like via x squared. So let's see if the neural network can predict that. So this neural network is only with one single layer. And so this is how the data looks like, the exact solution, and the training data are the dots, scattered points on top of it. So I will train the neural network with this data set. So I have my data. So next is which kind of model I have to use. So usually you saw it's a connected forward model, right? You have several layers which are connected to each other. So how you do is that you call a module called Keras from TensorFlow, and I say I need a sequential model. So this is the line, I say it's sequential. So I call this first, and then I add my next layer. So here I need only one input layer, so which is in the second line. So what I do is that add a dense layer with 32 input neurons and one input. So this is given by the input shape. So I have input of first layer with input shape 1 and 32 neurons. And then the output, because output is Y, it's again of the shape 1. And this is the output layer. So it's a very simple model. So with one layer, nothing complicated. So the next step, I define my model. So I have to train it. So what do? I have to first compile the model. So the next step is you compile the model. So for that, you call like something like model.compile. And then you define the loss and the optimizer, how do you want to solve this problem? So what is loss? So loss here is, we can take different kind of loss, but for a regression problem, usually we choose a mean squared error loss. So what does it mean? It literally means you take the mean of the square of the error. So the square of the error means, so here you have the input data, which you know how the Y should look like. For the X, you know how the Y should look like. And then Y hat is the prediction by the neural network. So ideally, the difference should be 0. That means the prediction is very good as the input. And the loss should be 0, but that's not always the case. So this is how, what you want to do is you want to minimize the loss. So how do you minimize the loss? So for that, you take something, you need to optimize it. So I will explain in the next slide. So you define something like an optimizer. And here I define Adam, but usually it's the best, it's a kind of gradient descent program, but usually if you start, you would see something like stochastic gradient descent. That would, what you will see is something like that. But Adam is just a modified, improved version of stochastic gradient descent code. So I will explain in the next slide. And you specify a learning rate, something like this, which is here I describe the learning rate to be 1 e raised to -2. So this is the basic thing. So so I will also explain this because it's important. So you need the gradient descent, right? So what you want to do is that you want to reduce the loss. And the weights, I explained to you what are the weights. They are the W's which you multiply with your input. So if you make a plot, you see that the loss versus weights will have a minimum. So we want to reach the minimum. That is, you want to find the weight where the loss is at its minimum. So how do you arrive at this minimum? So usually you find a point at the somewhere in the loss, and you take the gradient, and then you go into the other and take the next step. So the next step defines what is your learning rate. So just remember that now we are taking a gradient. So gradient means derivative of the loss with respect to the weight, right? So these things, the machine learning libraries like TensorFlow can do very fast, but I will explain also a little bit later if I have time. I think I'm already going very slow, but I just want you to understand these things. So this is something the machine can do, but this is what's happening. So we have to minimize the loss. So, and we have to find an ideal learning rate. So what we do is we find and we update the weights after every learning step or every training step. So the weight is weight minus learning rate into and this gradient of the loss with respect to the weight. So how do you find a learning rate? So here, if you see in the leftmost figure, the learning rate is very slow. So if we go, it means that it will take forever to reach the minimum. So then we increase the learning rate. But if it's too high, we never reach the minimum. We go to this point and then we jump the minimum and go to the next point. And so the code will never find your minimum loss. So the point is to find an ideal loss, so ideal learning rate, so that you reach this minimum in a nice, you don't miss this minimum, not too, and you reach there not too slow and not too fast. So this is what you have to, once you have the code, basically this is what you're doing. You're adjusting the hyperparameters. So the hyperparameters are the weights, the learning rate, and so on and so forth. So then you so you compile, you turn, you wrote the code. I mean, you wrote the model. So now you want to train the model. So for that, you have your input data, the corresponding output data, and then you train it for 500 steps. So we call it epochs. And for now, you don't have to see this callbacks. I mean, these are all advanced functions for plotting and stuff, which you can do. Anyway, so I also skipped batch size. So these are just simple codes. So I mean, just to show simply how you can write a code. So you take your data, and then you train the model. So for that, you do something like model.fit. And then you can evaluate the model. So once the model is trained enough, you evaluate the model by testing it on a test data. And then you see how good your prediction is or not, something like that. And then once you are happy with this, you can use your model to predict data for something which you don't have. So you want to predict something new. So once you are satisfied until the step 4, you can go to step 5. So this is basically how machine learning code works. So okay, this is just to show how the layers of our current model is there. So you have one input with 32 layers, 32 neurons, and then an output with one neuron, and the input to this layer is 32. So this is just to visualize. So you have all these functions to visualize. And then here I just wrote all the things which I just told you in a compact manner. And then I run it for 500 epochs, which I'm not showing here. So it's just that you run. So the code, it's literally 5 or 6 line of code, your machine learning code. So what does it look like? So it was a simple thing. So the output is like this, which is actually expected because the exact solution has the form x square parabolic, but the prediction looks like a straight line, and prediction with the training data is also not very good. but that's expected because you just you did not give anything. You just gave one layer, and it's like a equation of line. There is no activation function or nothing because it's just one layer and one output. So you have to improve your model. So what you do is you add several layers. So this is with one input, one output, and two hidden layers. And each of these layers have 132 neurons. And again, I use the same, I did not change anything. I just, okay, now I have activation functions, which I showed you before. So now the activation for the hidden layers are like ReLU. So this gives access to the so this gives non-linearity. So now the machine learning can see the non-linearities in your data. I mean, it's not always straight line, right? So this is the complete code, and what's the output? So here the output is actually very good, but that also is but that's also because I took the data through the entire set from -50 to 50. The training data comprises everywhere, and the training is very good, and it's able to predict. I mean, it's a simple data, so the prediction is quite good. But if I want to predict a data from where it has not seen it, because I have few data and I want to predict somewhere far away from somewhere where I have no collected data. So you will understand what I'm trying to say. So for that, it's the same code, only the data from now I take until only in the left side of the curve. And I don't know anything about the right side. And I trained the neural network with some data which I collected on the left side, but I have no idea what's happening in the right side. So the prediction is good where the data was there. So it's like the left corner you can see with the dots, the prediction is good. But I wanted to predict through the whole set where I don't have any collected data and I did not train the model. The model did not see any data here. So here the prediction is quite bad actually. So this is where it's a simple problem, but this is where our physics informed neural network actually comes. So this is, again, I try to predict with another set of data, but the prediction is quite wrong. So on the left side, the prediction is closer, but on the right side, it's trying to predict as a line because it has no idea what it looks like here. So here in this figure, I summarize all these things, the two models, but the last two are with two different kind of data. So the first one totally fails. The second one, after several iterations or epochs, the machine learning code is able to predict how it should behave. But for the third one, it's totally at a loss for the right-hand side. So this is where, if we have something like this, probably we can use something called a physics-informed neural network. So before going to explain what a physics-informed neural network is, I would like to explain what is automatic differentiation. In fact, the availability of automatic differentiation is what actually boomed these kind of codes, machine learning codes. So it's simply you want to differentiate a function. So normally what do? You either do it with a symbolic method, like you use something like Mathematica or something to get a symbolic solution, or you use numericals methods, for example, finite difference. But you know that with finite difference, if anybody worked in that, you know that to calculate the higher order derivatives, you need really dense grids. Otherwise, it's not, you don't get an exact result. But with automatic differentiation, it's a very simple thing. And you don't get all these problems. And I will explain briefly how it works. So for this, you need to understand the concept of dual numbers. So what is a dual number? So a number of the form a plus b epsilon is dual if epsilon square is equal to 0. So if you have something like this, it gives you very interesting results. So if you have a function f of x equals x squared plus x plus 1, and you evaluate this function at its dual number x plus epsilon, you can see that it's simple arithmetic. You just put x plus epsilon square, x plus epsilon plus 1, and you just separate it. So you see you got an output, which is the function itself and its derivative. The terms with epsilon is actually the derivative, right? So 2x plus 1, the derivative of fx. So if you evaluate a function at its double, you get the function and the derivative for free, the first derivative. So this is actually, I found it very interesting. I mean, it's a nice thing. And yeah, so how does automatic differentiation work? So for this, what you have to do is like you take, you create a computational graph or the Vanguard list of the function. For example, you have y equals x1, x2 minus sine of x2. So this is your function y, which is the output, and you want to calculate the function at x1 equal to 2 and x2 equal to 3. Yes, of course, you can put it this here and calculate, but another way to calculate. So you create something called this graph, and for this you have these nodes. So the first node V1 is the input x1. The second node is the input x2. So these two nodes become x1, x2 for V3 is x1, x2, right? You have to just follow the arrows. And V4 is sine of x2. So V5 is the sum of V3 and V4. So this is what automatic differentiation does. Like it splits a function into its using addition, subtraction, sines, causes, and whatever. And then it creates this computational graph. And then what do? So we have, and this step is and then we give the value. We want to evaluate the function at x1 equal to 2 and x2 equal to 3. So in this you evaluate by something called the forward pass. So we have these nodes V1, V2, V3, V4. So you just put the value and V5 and you got it, right? But now you can also calculate the partial derivatives by something called the backward pass. And what you do is for this, you calculate the partial, first what you do is you calculate the partial derivative of each node with respect to its immediate input. For example, partial derivative of V5 by V4 is -1, right? If you see from here, V5 by V4 would be just -1 here. So, I mean, it's simple. I mean, it's literally, you calculate the partial derivatives and you can just calculate by hand. It's quite fast. And then now you want to, because our original aim is to calculate the derivative of the function at x1 and x2, the first derivative. So now you simply use the chain rule. So we all know the chain rule. So di-f by di-x1 to calculate, you need V3. You just check the immediate nodes. And so you have V3 and the partial derivative of V3 by V1. So, I mean, it's if you look like this, maybe it looks a little complicated, but if you just sit down and write on by your own, it's really simple. And then you actually get the partial derivatives because you already calculated the values at each node. And then the partial derivative is just one simple chain rule. So this is actually what the automatic differentiation is doing. And this is how our machine learning code is also optimizing these weights, because here F would mean the loss and different X1s would mean the weights W, which if you remember. So this, and then it's called backprop, and then you are doing this continuously. So to do by hand, it's a little bit difficult. So that's why, but the computers can do these kind of problems very fast. So that's why this machine learning community sort of boomed when we got better algorithms to calculate derivatives. And so TensorFlow, PyTorch, and these are able to do this differentiation. They have inbuilt libraries for that. You can also write by hand, but you don't need to do that. So this is the fundamental of the whole of machine learning, the fundamentals. So you can say you now know how machine learning works. So just to show how you would write in a TensorFlow, how a TensorFlow code would look like. So you have this gradient. So now in TensorFlow 2.0, you call something called gradient tape, and it's like you are recording it. So you ask it to watch the x's, which we defined here. And then you just simply write y, and some function, sigmoid function, and you want to calculate the first derivative. So it's simply gradient of y comma x dy by dx. And yxx is again gradient of yx by x, right? dy of x. So, I mean, it's simple 2 lines of code. So, yeah. So this is just a plot to show how the derivatives look like. So you have y, which is a sigmoid, and then the first derivative and its second derivative, and similarly you can calculate so on and so forth. So you can do. So this is much better than using some finite difference where the accuracy would be not so good. Then you would need really dense grids and such. So this is just to know. You can also probably find application to do. Yeah, what's this? Somebody writing on my screen. Anyway, I don't know how to clear this, but apparently it's not me. Anyway, let me try to clear. So these lines on the screen are not me. If you see this, if somebody was sharing, please stop it. Yeah, okay. Because anyway, so now let's see what is, ignore these lines, this annotation, because I'm not able to clear. Let me try for 1 second because I'm already. Maybe undo? No, because it's not me, so I cannot clear it. It's so anyway, let's see. It does not matter. So we have the model 3. So this is my physics informed neural network. So this, if you see the plot here, you have you have some data, right? Like these red circles are your input training data. And then, but ideally the exact solution looks something like a wave, right? Like this. And then you predict it. So the standard neural network, which you saw until now, is able to make a very good prediction. But in the range afterwards, where it has no data, it's not able to make any prediction. The prediction is literally very bad. So this example, I actually adopted from this blog. You can read this blog, and he also put his codes there. So it's very beautiful. And yes, to understand it really clears the difference between a standard neural network and a physics-informed neural network. So then what do? So you want to actually see what happens to this complete area. You want to predict that, right? Krishna Priya. Oh, yeah. So now you have something called the physics-informed neural network. So what does it do? So when I look at this curve, I say that even though I have some data, but I think that maybe it behaves like a damped simple harmonic oscillator. Probably. So so I'd say, okay, it behaves like this. So I give the neural network the physics. That is, I say that it behaves, it has to behave like this equation. And I constrain the neural network together with this physics. So when I do that, you can see the blue curve. It actually fits the ideal solution or the exact solution, even though it did not see data there. So this is why we want to use physics-informed neural network, where we have few data and we know some physics. So in this, some data, not few data, we have some data and we have some physics. So when we have this scenario, we can actually use the physics-informed neural network. So how does it work? So this is a Nature Review Physics from June 2021. And I took the picture from this, and Karniadakis et al. So these were the guys who also wrote not the first, but the paper which actually became really famous in 2019 or 2017. So this, so what do you do? So this section, this square, the neural network section, and that's what I was talking about until now. So here the neural network x comma t and theta are your hyperparameters, the weights which we talked about earlier. So you have two input here. They are trying to solve this equation, something like du by so it has derivative of t, derivative of x, derivative with respect to x square. So this is where, even though the automatic differentiation is already doing inside this, now you also know that you can use it for finding the derivatives of the function. So what you do is that there is something called the universal approximation theorem, which says that any neural network can approximate a continuous function. So we say that this neural network is, the output is u and is equal to and this is the function, this the f of u, this equation. So not f of u. So this, we equate this neural network to this physics, this equation, because it can approximate very well this function. And then in the neural network, we are already trying to minimize the losses, but now we add also the physics laws. So what are the physics laws? So we have some data, like we probably would have the input, we probably would know the input condition, what it should be, and probably we know the boundary condition. So we will minimize that. Plus we would also minimize the equation itself, the loss in this equation itself. So when you club all these laws, this neural network is working together with the physics of the system. So you are able to really predict very good solutions, as I showed you before. So why it's important? So so this is a paper written, not how, I don't know how to call it, a report by the prepared for US Department of Energy. So in this you can find, so now they call it a scientific machine learning. So, but it's basically the same thing. It's the, so you use the physics of the system to solve different problems where you have some data. So for example, here you have the weather problems and other things. So this is for a power grid. And yeah, so all these things. So this is just the cover page and you can find this. So this area is like really becoming very important because in many scenarios, we are not able to collect a lot of data, but we know some physics of the system. So we try to use that, and we use this new scientific machine learning or the physics informed neural networks to solve our problem. So I'll just simply show from their paper, from Raisi's paper. So this was the author, Karnidakis is the last author. So they were from Brown. So this was the paper. Okay, I did not write the year. It's from okay, they wrote in 2017, probably published in 2019. So I forgot to write the year. So this is from their paper. So this is a nonlinear Schrodinger equation. So something like you have u, variation of u with respect to time, and variation of u with respect to x, right? And this is the equation. So you have, the input that you probably know the input at x, t equal to 0. So ideally we know the solution to be sec hyperbolic x of this system. So we know the input, and we also know the boundary condition, that is that at the boundaries the solutions should be 0. So this is the only thing we know. So these stars are the input for the physics informed neural network. So this is the only thing we actually know. But with this, we are actually really able to predict the solution. So if you see, the red and the blue are exact in the prediction. So they fit really well inside. So this is because even though we have very few data, we actually know what is the physics of the system. So when we impose this constraint, we are able to actually do it, get good results. So Yeah, I wanted to show you the next slide, which actually probably, wait a second. Yeah, so this is another example. So it's also from the same group, Karnadaka's group. It's a science paper. And here they was showing the fluid dynamics of the system. And like, so this is some kind of pipe, and then they use Navier-Stokes. They know that this system should behave like a it's a Navier-Stokes system, and then they use these constraints into the neural network and are really able to predict how the solution should be. So these are like really good results. And then, I mean, people are using all the people are using everywhere for all sorts of problems, because it's not always possible to have a lot of data with experiments. I mean, you are not, but you know the physics of it. So for us, what we are trying to do is that for optics, if we want to predict some properties, so we have some experiments using FDTD or something, so some data or through experiments, and we collect them and we try to predict it. So that's something we try to do. So to summarize, so PIN, so physics-informed neural network, is a neural network which can be trained to solve supervised learning tasks. So it respects the underlying laws of physics based on an ODE or PDE, so linear or nonlinear. So in their original paper, they also showed that if you have enough data and you don't know that much of the physics, you can also infer new kind of equations, new kind of physics through this kind of neural network. And so basically you use it when you have some data and you have the, the physics. So this is the reference. I missed the year. And yeah, so as a final remark, I briefly introduced what is an artificial neural network, showed you some simple examples as to how to use neural network for predictions. Then I introduced you to automatic differentiation, double number. I find that concept very interesting, and introduced PIN and physics. So PIN is increasingly becoming important in several scientific areas. And already NVIDIA and ANSYS are using PIN. So the guy, Raisi, he's already working with NVIDIA. And NVIDIA also has a, how do you call it, a software, SimNet. So you can download it and you can use it in GPU-enabled systems to solve your physics-informed problems. So thank you for listening. Questions, comments, anything? Yeah. I think I get 45 minutes.
Also, a comment, very sorry for the always part, some interruptions that's on the Zoom screen, very sorry.
No.
Thank you, Dr. Jisha. It was a very informative talk, covering from the very basic to very advanced part of neural network. Now the session is open for discussion. If you have any doubt, you can either unmute yourselves and ask questions, or you can write in the chat box. Yeah, some questions are already in the chat box.
I can. So Shweta is asking, what exactly happens when using ReLU on the variable y? And can you please explain more about the activation function? So this was here, just to show the slide where it is. Yeah. So with ReLU, what we are trying to do is like, because here, what we are doing is that you have the function, right? Wait. No. I always make this mistake because you have to select the area to find that if you want to. So ReLU, what it does is actually everything below 0, x equal to 0, it has to put it to 0. And then only when you achieve like certain threshold, you want to activate the function. So what it does is that everything below x negative would be 0, and everything above would be positive. So it sort of is making like it would sort of try to classify things. It's actually cutting stuff which is not enough. So I mean, it's literally that what it's doing, like you just apply that function. So if you want to ask more physically, I don't know, I mean, what but this is what it does. Like it literally cuts the all the weights which are less than 0, and adds only which are above certain value. So you try to use this kind of function instead of this, which is like a sudden jump. So you try to use something like this. To explain more about that. So because yeah, the activation function is like, I mean, okay, I'm also not an expert, but to how to say, because you want to, because your system is non-linear, right? So if you don't have an activation function, your neural network never will see the non-linearity of your data. So and then given you have all these layers are connected, and you if you adjust weight of one of the layer, it will propagate throughout the layer. So this is, so the activation function actually helps us to introduce non-linearity into the system. So if there is no activation function, like in our simple first model, you will always see a straight line. It doesn't matter how many layers you have, you will always see a straight line. So you have to choose a proper activation function depending on your problem. So for regression problems, usually you use ReLU. And if you want to use classification, you have something called softmax, and because then it divides. So these are like different, I mean, yeah. So you need an activation function to have a nonlinearity in the system so that the neural network can see the nonlinearity of your data. So if I can answer the next. So Manoj is asking, adding to the previous question, how is spin useful in studying geometric phases? Yes, that's what we are trying to understand. That's also our problem. Like we also want to like somehow use it for our problem, which probably Manoj knows that we are working on geometric phases. But it depends. I mean, because it's not always, because it's fashionable, but it's not always useful. But sometimes it happens that the problem itself is so complicated that your finite difference solutions, you need so much the grid size and the stability is so bad, because in our case we are rotating the system, and it's, so if we have some set of solution, probably we could use it for pin. So yeah, I don't have a straightforward answer, but yeah, that is something could be used, like, because it's simply this. For example, let me tell you with a simple example of like Helmholtz equation. So you know, so, because you only need the input solution, input gas, let's say, if you don't have a solution, and how it should behave at the boundary. So at the boundary, probably you want to say, so most of our problems, we are working with fields, so the field should go to 0 at the boundary. So like I showed for the NLSE. So the problem would be like that, I think. Yes. Yeah.
Any other questions?
Any other? Okay, there was a question from Krishna Priya, which I actually missed. So what are the current major applications of physics-informed neural network? Is it convenient to use PIN in major research fields? So in fact, the last few slides which I showed probably answers the poster from the US, this poster. So it's like in fluid dynamics, it's heavily used. So in the company NVIDIA, so they make these graphic cards, right? Yes. So then these chips or whatever. So the problem for them is they want to understand how the heat is dissipating, right? So these problems are really computationally intensive. So there they are using it to design novel chipsets and such thing. In fact, even the new phones, the Google Pixel 6 Pros, they have their own chipset, which is neural, how to say, AI informed. So not physics informed, but it's so it's actually in the, let's say, in the last couple of years, physics informed neural network is really a major field of research for everybody. And to use this, as I said, you need some data and some physics. So if you don't have data and you don't know about the physics, this is not a solution for you. Or you have a lot of data and no physics, you go to the standard neural network. But the case where you have some data and you know some physics about it, like maybe this system has Navier-Stokes equation or some fluid dynamic equation or a wave equation, you can actually use spin. Yes. And yes, it's very convenient if you are in this region, like some data and some physics is known. So for example, these are all different research areas. I actually do not remember each of them from the figures now, but the back, they have if you look at this paper or a book article or a collection of all these things, you will find that a lot of research area is using this. Yes. Any application?
Other questions? Let's end the session. Thank you, Dr. Jisha Supi, for being with us, your valued time with us.
Thank you. It was
It's a very emerging field, the physics-informed neural network. On behalf of Dharamada College and also behalf of Trident University, and of course from my part itself, I give you a very big thank you.
Thank you. Thank you all. Thank you for listening. So are we ending the session?
Thank you, ma'am, for chairing the session. It's my pleasure to thank Dr. Jisha, who, despite her busy schedule, has found time to grace this lecture. By now, we've come to the end of the session. Once again, I thank each one of you for making this plenary more delightful with your presence. I humbly request every one of you to join the next session at 4 p.m. Thank you.
Recording stopped.
Hi, Ji.